23 of CH 576, and in the last class we had started doing this Brownian motion theory. Okay, so we'll start from there. Just to recap, we're talking about, for example, a motion of a colloidal particle or a pollen grain, or could be even a molecule inside in a solvent. A big molecule could be a protein molecule actually in water. This is the one, the yellow one shown here, and this is executing what is known as uh, Brownian motion. So, and if you follow one of these particles, you see that the trajectory is completely random or zigzag. So this is Brownian motion at the single particle level. I can think of n particles, then people talk about diffusion. So diffusion is a manifestation of each particle doing random walk. That is diffusion. Diffusion is nothing but random walk. And we had done this, we did the original treatment of Einstein. We did it in one dimension. Remember this picture. At time t, we start with the position x plus delta. At time t plus tau, we have a position x. Then what is how the distribution changes from here to there is given by this. I multiply this with some jump function, integrate over all possible jumps. Jumps could be negative or positive. Jump is this delta. And then we end up deriving this equation, which is called Einstein diffusion equation. And you know that it looks exactly the same when you talk about the time-dependent density of a liquid. This is called Fick's second law. I think some of you may know Fick's second law. I hope it is taught somewhere. So this equation is equivalent to Fick's second law. How many of you know this is Fick's second law?
Yes, sir.
Yes, sir.
Yeah, it is Fick's second law. And then we solve this equation. I said that this equation has the same structure of Schrodinger equation, but the Schrodinger equation, usually what you do in Schrodinger equation, the usual treatment, that you solve it as a boundary value problem. Okay, you split this into time and space part, and then you solve the space part as boundary value problem. But here you have to solve this equation not as a boundary value problem, but as an initial value problem. Okay, so the initial condition is this: that density, the probability density at time 0 is actually delta function. I multiply this with n just to make it more general, that you have n number of particles. So this is a Dirac delta function, and I hope you remember that we actually derived this equation. We did Fourier transformation, went to the reciprocal space of x, which is k space, and then we came back to the real space and we derived this. We solve the equation, and the solution gives you here is a solution. This is a Gaussian distribution of your density, Gaussian in position, and with this you can calculate average displacement, which is 0, but x square average, which is your mean square displacement, is equal to 2 times d times t, and d is called diffusion constant. Okay, I stopped here, and I had showed that if you had dynamics which is governed by inertia, then for example a particle moving with a constant velocity, the displacement is actually velocity times time traveled, so v times t. So displacement is proportional to t, but here the displacement square, average of some displacement square, is proportional to t, which basically means the displacement is proportional to t to the power of half root over t. So this is much slower than the ballistic dynamics. The scaling is different. One is t square, another one is t for the mean square displacement. Okay, and we had stopped here. So we'll start from here. Before we do something, let us try doing this here. So the idea is as follows. Okay. Today I'm going to talk about this diffusion and mobility in detail. So, and then we'll describe the motion at the single particle level. So we will do the treatment in one dimension. I have only one dimension x. There is no y or z, to make your life easy. So you can think of a particle, okay, moving under the force, the gravity, the force of gravity, okay, in one direction, x direction, in a liquid. We have a immersed colloidal particle moving under the gravity in liquid, and the F is the gravity, the force of gravity. And of course, you have in one direction, x direction, only one dimension. One dimension problem is okay. This particle is spherical. The spherical particle of radius r, and it is moving under the force of gravity in a liquid. Okay. Could be water. So you can think of a colloidal particle immersed in water. It is size spherical in shape. It has radius r, but in one dimension, just to make your life easy. Okay, and this liquid has a viscosity, so you can just call it, say, eta. The coefficient of viscosity is eta for this liquid. This eta is coefficient of viscosity. Now this, this gravity is pulling the particle, and the particle is going, and it is also experiencing a drag in the opposite direction. This is called viscous drag experienced by the particle, and this viscous drag is given by 6 pi eta r into the velocity of the particle. So I'm calling it, so want to call it, we call it v0. Okay, and this is viscous drag, and then when this external force uh, force matches with this viscous drag, okay, balances the viscous drag, then the particle moves with this velocity v0. Which basically means that my f is 6 pi eta r v0. Okay, and this relation, that viscous drag is equal to 6 pi eta r v, it has a name, this relation. How many of you know this?
Stokes relation?
Yeah, it's called Stokes law. Okay, for a spherical particle, it is like this. Okay, so now if I assume that, okay, if so, essentially it tells you that it gives you v0. Now if nu is the number of, now I can think of many particles, every Each of them is executing this random walk. Huh? Particles per unit volume. Then, if I multiply nu with V0, nu is the number of particles per unit volume. Multiplying with V0. V0 is displacement divided by time. So V0 by volume is something like area divided by time, isn't it? Number of particles per unit area per unit time. This one. Is it clear? The nu is the number of particles per unit volume. So you have some number of particles divided by volume. And V0 is displacement divided by time. So this displacement and volume will partially cancel each other. It will give you 1 over area. And you have also 1 over time because of V0. So this basically means that, okay, this is the number of particles passing through a unit area through a unit area per unit time. Okay, this is how it is. So this gives you the number of particles passing through per unit area per unit time. This is given by nu into V0. So it basically means that you have nu F6 by eta R. This amount, this quantity is this. Okay. Now this is actually, then I write down what is known as, if I write something like minus d times this d nu dx, you know, this is called fixed fast law. This fixed fast law. This is called diffusion flux. Okay, and this is what? This is exactly the same thing, no? Number of particles per unit area per unit time. So now if I can just equate these two. What is there on my left hand side? Okay. Now one thing you know that if is a force due to gravity, no? And you know from your school physics that force due to gravity, this should also have because of this force due to gravity, the density. So if I go higher in altitude, air becomes thinner, isn't it? The density decreases because of this gravity, due to this gravity. So and then if you have some kind of equilibrium, then you have some Boltzmann distribution. So you'd expect something like a Boltzmann distribution. Now, what is Boltzmann distribution of this nu? Remember what is nu? Nu is the number of particles per unit volume. What is that? This is density. It's nothing but density, no? Now, can anyone tell me how this density will vary with height? That is given by Boltzmann distribution. No, how do you write that? Can anyone tell me?
E to the negative beta potential due to gravity.
Yes, it is actually, it should be something like nu is something like nu 0, and then you'll have exponential factor, no? Minus, you know that minus beta E kind of thing, isn't it? So your E is your force into displacement x minus x0. So it is between 2 points x0 and x. This is your energy, and then if you multiply this with Avogadro number, let me multiply the Avogadro number, and then I should divide by not kBT but RT. Is this clear? This expression.
Yes, sir.
It's very simple physics. This is also Boltzmann distribution. Now I go back to this equation now, the one I have written on my left. If I go to this equation I can write it again. It is going to be minus d nu by nu, and I go from say nu 0 to nu is equal to 1. Sorry, minus I've taken here. This is uh, uh, f, and then nu have taken on the other side 6 by eta r into d, but then I have dx, and the dx varies from what? X0 to x. Since this is x, I should put Diamond variable. Anyway, so what is the answer? On the left hand side, I'm going to get ln. Tell me, I'm going to get ln
mu by mu 0.
mu 0. If I take the minus on the other side, minus f this also gives you, this. Sorry. This one divided by, I have 6 by. Now I can compare these two equations.
Yes.
If I compare this to what I'm going to get, so this equation I'm calling it say equation 1. This one I'm calling it equation 2. So comparing 1 and 2, what I get?
B equal to RT by 6 by eta r.
Compare 1 and 2, you're going to get just let me write down. Exactly, this is what I get, isn't it?
Yes.
Okay. Now what I do, I am redefining something. This quantity, I'm calling it B. And B has a name. This is called mobility. Now mobility is something, you just look at it. If you have a bigger particle, this mobility is small. If your viscosity is high, mobility is also small. So if I write this is a mobility, then I can say that your diffusion constant, D is your diffusion constant, no? Or diffusion coefficient. The diffusion coefficient D is given by then Na by RT into 6 by eta R. What does it mean? It will be RT by Na into V. Okay? So this is a relation between the diffusion constant and your mobility. But you know what is this? D is nothing but then KBT into B, isn't it? Or D is KBT by 6 by eta R. Is this fine? And this has a relation. This relation has a name. This is called Stokes-Einstein relation. And this is maintained most of the times. Your diffusion constant of a particle diffusing or doing random walk in a fluid is 1 over R, 1 over its radius, spherical particle. Also 1 over viscosity of the medium, proportional to temperature of the environment, medium. And this is the exact expression. And this is called Stokes-Einstein relation. Okay. I hope that I don't know whether you knew this, but anyway, this relation actually one can use to determine your Avogadro's number, and people have done it long back, and they have found good result. So I'll just write down here. Avogadro's number, Avogadro number. How do you do? Because you know that your D is given by Ft by Na 1 by 6 by eta R. And you remember from the previous class that your lambda x is 2D T. Remember this, no? Because you had this, no?
Yes, sir.
And this one is, and this one I'm calling it lambda x, displacement, average displacement. So if I put this back here, it is going to be root over 2 into T, then Ft by Na whole to the power of half. This is the expression. And actually one can use this expression to find Na. And lambda x you get from experiment. Experimentally one can measure. And you also know viscosity, you know, known for liquids. No, for range of liquids, you know what is the viscosity. So if you put this, then you can find out the Avogadro's number. Okay? I hope this is clear. This is
Yes,
not
sir.
very difficult so far. So we move to some new topic. And the topic is that, okay, now what happened at the single particle level, the description. So if I tag this particle, this is the single particle, it is doing this random walk. So let me write down, for example, if I write down the equation in such a way that, okay, m is the mass of the particle, dv dt, you know, this is Newton's equation kind of thing. M times dv dt is m times acceleration is equal to force. No. And for the time being, say, let us assume that when the particle moves, it has only the viscous drag, and it is acting in the opposite direction. So it will be minus 6 pi eta r into v. Is this clear? And I stop here. Let me write down this way. And the particle moves and it only feels this viscous drag from the fluid. And then the mass time acceleration should be equal to the force. This is force. And what I have written here is nothing but Newton's equation, isn't it? Hope you understand this Newton's equation.
Yes, sir.
The force balance equation, nothing else. It's just a force balance equation. Now, if I solve this equation, I know how to solve it. It is exponential decay. By m into r. This is how it is. Minus 6 by eta r by m into t.
Yes, sir.
And or in other ones, ln v by v0. So I want to calculate t10, t110. So the time taken for the particles to start with the velocity v0 and so that the velocity becomes v0 by 10. So what is then the ratio v by v0? Basically means v by v0 is what? Tell me.
T to
What
the minus 6 by 8 or T by n.
Ey v0 is 1 by 10, isn't it?
Yes, sir.
This is what exactly. So I put it
Yes.
here. If I put it here, so it is going to be ln 10, because and if you do the calculation, your T 1 by 10, I'll tell you the value. So take some platinum particles. This is real values I'm giving you. So you have tiny platinum particles immersed in water, and these particles are about this size, 10 to the minus 6 centimeter. Okay. Your eta is 0.01 poise for water, and this mass of these particles are 2.5 10 to the minus 15 gram. Okay. And then if you put it here, then T 1 by 10 is fine. I can write down the number. It is 3.3. You can check. Which basically means 10 to the power minus 7 second within a very short time. So the particle velocity very short time. The particle practically nearly completely actually its original velocity. So actually the particle comes to almost stagnant position, isn't it? It stops moving almost within very short time. But this does not happen in reality, because if you try observing this colloidal particle or pollen grain under the microscope, it keeps on moving, isn't it? It is all the time is moving. It never stops. But if I follow this Newton's equation, then it should stop within fraction of second, within very short time. But it does not happen. Is this clear to all of you? It does not happen.
Yes, sir.
But in reality, it does not happen. So what is the solution? And so basically, it means that there should be a mechanism by which this particle velocity, the particle remains rather alive in a way, isn't it? It doesn't stop. So it basically tells you that I have to go back and I have to check my Newton's equation. I'm doing classical mechanics, but this Newtonian description is not complete here. It is incomplete. It is not correct. So what should I do now? Actually, the solution is as follows, because if you think carefully, when the particle moves, this colloidal particle moving in this fluid, water, this water molecules, they are colliding with this colloidal particle and they're transferring some momentum. No? They're colliding, and they're colliding randomly, isn't it?
Yes, sir.
Water molecules, they're colliding with this colloidal particle randomly. So they are exerting
Random kicks.
random kick. So random kick onto this colloidal particle. So you have to take care of these random kicks. So we had this earlier, but this is not the complete story. I have to add some function of time, which is a random kick. This is a random function of time. So it's a random function of time. Okay. This is also called noise. And it has a property that if I take average of this noise, This is a random number, no? It has to be 0. And we assume that, okay, if I take average like this, ft and ft prime, then it is something like, say, 2 times some constant c delta t minus t prime. So only when your t and t prime are very, very close to each other, they are actually same, then only they are correlated. Otherwise, these random kicks at 2 different times, they are uncorrelated. Is this clear?
Yes, sir.
Yes.
This is my equation, and this equation is a name. This is called Langevin equation. It was proposed by Langevin in 1908. This is by Paul Langevin, a physicist. Yeah, somebody has a question. Of course, this equation assumes that there is no external force acting on the particle. There is no external potential. You can have some external potential, no? But there is nothing. There is a free particle diffusing in a fluid, colloidal particle. Is this clear? Is this clear?
Yes, sir.
Yes, sir.
So what is my equation of motion? My equation of motion is there. So let me use some other color. Okay, maybe the green is better. This equation of motion I'm writing again, rewriting the equation of motion. M x double dot is equal to minus 6 pi eta r x dot. Is this clear to all of you? Because x dot is v, x double dot is v dot, which basically means ddt. Is this clear?
Acceleration.
Notation should be clear, no?
Yes, sir.
So now you take this and now multiplying both sides by x. If I multiply both sides by x, what I'm going to get? I'm going to get m x x double dot is equal to minus 6 pi eta r x x double dot plus x ft. Okay, and then I do one thing. I can rewrite this equation as x x double dot minus 6 pi eta r by m okay. I can write it like this. Is it clear that I can write it like this?
Yeah.
And let us name this part. This part 6 pi eta divided by m. So let me call it something like gamma. If I call it gamma, then how does it look like? My equation now looks like, I go to the next slide. My equation looks like x x double dot is equal to minus gamma x dot plus 1 by m x. Fine? Is this fine? Now,
Yes, sir.
now these few things you should know. X square dot. What is this? This is ddt of x square. What will be the answer? It will be 2x x dot. Is this clear?
Yes, sir.
Yes, sir.
This is fine. So if I take x square and then double dot on that, what is this? This is actually second derivative with respect to time of x square, isn't it? Which basically means ddt of 2x dot. This basically means 2 x dot whole square, because you have x dot, then x dot, plus 2x x double dot. It's fine. Is this clear?
Yes, sir.
So this basically also tells you that if I write this x double dot, you can see why I'm doing this. This one. This has to be half x square double dot minus x dot square. Fine? Is this fine to all of you? It's good to put a bracket here, just to not to confuse thing. Eh? The order of dot and square is important. It should be. It is fine, na? Any problem? It is very simple. Anish?
Yes, sir. Clear.
Fine, no? This is very simple. So I'll replace this with this. So I am going to have half x square double dot minus x dot whole square is equal to minus gamma x dot plus 1 by m x of t. Is this clear? Should be clear.
Yes, sir.
I'm just multiplying both sides by 2. Just okay. I hope. Is this clear so far? I
Yes,
hope
sir.
I have not done anything wrong. Did I do anything wrong?
That will be gamma x x dot.
Sorry. This is fine, no? This is gamma x dot, no? I think
Yes.
one I missed, no? That's what. This one, no? This was like this.
Yes.
Hmm? Okay, this is, and what is x dot is x square dot by 2, isn't it? So it gives you x square double dot minus 2x dot whole square, and this is, you know, that is gamma, and 2x dot. 2x dot is x square dot, isn't it?
Yes.
Is fine. Now I take the average on both sides. If I take the averages on both sides, what I'm going to get? I'm going to get, this is second derivative of this. You had x square, no? Replaced by x square average. Minus 2 x dot square average. Remember, here dd dot is outside. Okay, I am just hoping you follow. Here x square double dot means second derivative with respect to time of x square. Then I take the average, isn't it?
Yes, sir.
Because if I write this equation again, this is nothing but like this, no?
Yes.
like this. I'm not writing on the left hand side. This is how it is. Now if I take the average, isn't it? What will be the on the left hand side? Minus gamma. Now this is x square dot. It basically means ddt of x square. No, I put the average here, and this one is average is here because both are function of time, isn't it? Like taking time average. It's actually taking ensemble average. So can now I'll go one by one. Now tell me what is this on the right hand side. This quantity x ft average. Actually, this is 0 because there is no correlation between position and random force. Because when the particle is here or here or here, that does not determine what will be the random force acting on the particle. Similarly, you understand now? So this correlation has to be 0. There is a correlation, no? The correlation between position at time t into random force at time t. Because position and the random force are uncorrelated. Because both are at the same time, taken at the same time. Okay, now what about other quantities? Can anyone tell me what are the other quantities? What about this? X square average?
Non-zero.
Non-zero.
Okay. What about x dot? X dot square? Now this is what is? This is not.
That also non-zero.
Oh, what is x dot whole square? Basically means v square average. What is this?
Square velocity.
Huh? How many of you know equipartition theorem? What is the answer?
Kinetic theory.
Gravity by 2.
Yeah. Hmm? What is this? This is 2 into kVt by m, isn't it? This quantity.
Yes, sir.
So end of the day, what I'm getting after doing this, let me go to the other page. It is better. This is what exactly you get, isn't it? This one, and I take this one, and then I take on this on the other side. Okay, this is the equation. Is it
Yes.
fine with you, all of you? It's not. It looks much simpler, isn't it? It looks much simpler. So let us assume that I'm calling it y. Okay, and this 2 kBt by m, this is something, some constant c, small c. I had put somewhere this is different. Okay, this is c prime. This is different. Okay, so then what will happen to this equation? This equation has become now the second derivative of ddt of x square, which basically means what is this? This is y dot, isn't it? Can I write y dot
Yes, sir.
plus gamma? What is this? Y. This is the equation. This equation now looks much better, isn't it?
Yes.
Okay. Now let gamma y minus c, let us call it y prime. Okay, this is not derivative. Okay, not a derivative, not a special derivative, just a notation. Gamma y minus y c is y prime. Okay, gamma y minus c is y prime. Then what do you have here? You have the equation is y dot equals to minus y prime. This is a notation, just a notation. Is this fine?
Yes, sir.
This is fine. Okay. Now this equation again, I take this. If I take y prime and then I put a dot, if I take a derivative of y prime, what I'm going to get? I'm going to get gamma y dot plus 0, no? Because if I take derivative of c with respect to time, is 0. Basically, y prime dot is equal to gamma y dot. I hope you are following. All
Yes,
of
sir.
this is fine. Now, what I can do, I can now put it back here. If I put it back here, what I'm going to get? I'm going to get y dot no, not y dot. Like, let me write down this. Y dot is actually equal to uh, 1 by gamma y prime dot y prime dot. Okay. So this one is like let me write down this way. It is better. So this is y prime dot equal to gamma y dot. But y dot is what? Y dot is minus y prime. It is minus gamma y prime. Is this clear? Because as y dot equal to minus y prime. Huh? This is fine, no? Should be fine. Can you solve this equation?
Yes, sir.
What? This is nothing. This is x dot equal to some constant gamma times x dot x, isn't it? If you solve this, what I'm going to get?
Exponential.
Yes, because if you solve this, what I'm going to get? Because you have dy prime dt is minus gamma y prime or dy prime y prime. Okay, so if you integrate this, so 0 to t, if you integrate this, say y prime at t equal to 0 to y prime, so this will give me, if I write down carefully, I'll get it, y prime equal to some constant exponential of minus gamma t. And this some constant is what? This is nothing but your y prime at t equal to 0. Is this clear?
Yes, sir.
We could follow. It is not very difficult. Now, if your y prime equal to a, so let me write down again. Then you remember what is y prime. What is y prime? Y prime was gamma y minus c. What I have here now is gamma y minus c, which is y prime. This is equal to a times to the minus gamma t. Is this clear? So this basically tells you that your y is, take on the other side, c by gamma plus a by gamma. Are you fine with it?
Yes, sir.
Can you recall what was y?
ddt of x plus x and x square.
Yes. There was the expression, no? So what I have here is ddt of okay. Now if I integrate, what I'm going to get? It's not difficult, no? If I integrate
Yes, sir.
x square average, first one will give me what? Some time, no? From 0 to t, no? Plus a by gamma is constant, you take it outside. This one you will integrate from where to where?
0 to t.
So what is the answer? You know, this is known as gamma.
E to the minus gamma t by minus gamma.
Now this gamma and gamma will give you a gamma square, isn't it? And the minus you can think. One is 1 and one is t. Okay, but you have minus, so you can absorb the minus. You can get. I think this is fine, no?
Yes, sir.
Your x square average okay. Now what is the relation between C and gamma? Can anyone tell me? Because your y prime at time 0 is A, isn't it?
Yes, sir.
And what is y prime? Y prime was gamma y. This is gamma
Minus.
y0 minus C equal to A. And what is y0? Y0 is ddt of x square. The whole thing has to be taken at t equal to 0, no? But you know x square average. So this has to be 0, no? Some constant, no? At time 0. This is 0. X square average, if I take at the 0 time, you have to put 0 time. Some initial average. So what I'm going to get? I'm going to get A equals to minus C. If I put like this, isn't it? This part is 0. A equals to minus C. So that will give me what? That will give me the expression for x square average. X square average now has become C by gamma T plus, it is plus, it is minus C by gamma. You remember what was gamma? Okay, gamma you can think of later, but what was C? Check your notes. I think this was
2
C,
kbt by m.
isn't it? So your x square average has now become square actually. And this is a general expression. This is actually general expression for the mean square displacement. No external force. So this is a general expression. Very nice. This is something which I really want. Okay. Now, when t goes to infinity, in the long time limit, it's called long time limit, isn't it? You go to long time limit, what do you expect here? What is the expression for x square average? Just by
X
looking
is
at this
proportional
expression.
to t.
Yes, because this exponential of minus gamma t should be 0, no?
Yes.
e to the minus infinity is 0, isn't it?
Yes, sir.
So your x square average will become gamma t minus, because it's 1 minus, because 0 is 1, it is 1 minus, sorry, minus infinity is actually 0. But you know, the long time, so this part is very small compared to this part, isn't it? Your x square average is equal to 2 kbt by m gamma. Okay? So if
Yes,
I
sir.
put the expression, you remember that 2 kbt by m. What was the expression for gamma?
6 by 8 hours.
Gamma was, no, 6 pi eta r divided by m. Just check.
Yes.
It was like this. So it is like
Yes,
2,
yes, yes.
2 kbt by 6 pi eta r. And you know what is this 6 kbt by this one? This is the diffusion constant. And this is exactly what you have had got doing this Einstein treatment, no? Sorry.
Yes, sir.
Langevin's treatment gives you the same result as that of Einstein treatment, isn't it? It's very interesting. Can you see? Exactly, this
Yes.
x square is equal to 2dt in the long time limit. In the long time limit, you get x square equals to 2dt, and it exactly matches with the Einstein's treatment, the Langevin's treatment. Can you see that?
Yes, sir.
So this is very interesting. A lot of physics is going there. We'll talk about it later, but we can do one more thing. What you can do, actually, you can look at what happens in the short time limit. Can anyone tell me what happens in the short time limit? When the time is very short, what do you do? Short time limit, what you should do to this expression?
We can further expand the
Actually,
exponent.
speak for it.
So actually in the short time limit, yeah, you're right. Maybe with this, short time means I can expand this exponential. If I expand this exponential, what I'm going to get
1 minus gamma t.
1 minus gamma t plus gamma square by t square by 2 factorial, like this, isn't it? Minus, I think. Okay. This is
Yes.
exactly what you get, no? Um, just I think better I go to the next uh, slide. It's better. Short time limit. Short time limit. And in the short time limit, your m gamma, no? One minus, I told you one. Minus will become plus gamma t, and then that plus will become minus, isn't it? What I'm going to get? This will be like this. So the first term will give you 2 kbt by m gamma t, and the next term will give you plus 2 will cancel kbt by m gamma t square, isn't it? I hope I have not done anything wrong. This term will again cancel.
Yes, sir.
So x square average will give you
So that should be gamma square t square, right?
sorry, yes, gamma square t square. So there should not be any gamma. Yeah, it is very important that we don't have gamma there. I was thinking. Thank you. Because it should be independent of the viscosity. Wait for a minute. The last line I want to write. Just wait for a second. So, but you can see that what is happening, your x square average is now proportional to t square, isn't it? It's kbt
Yes,
by
sir.
m times t square, which I'll write in a minute. I have some problem with writing. But this is in the short time limit. For the long time limit, it is different.
So can we say that the motion is ballistic in the short
Yeah,
time,
it's ballistic.
and
It is
diffusive
exactly
in
what
the
I
long time?
want to tell you. So this is ballistic or inertia driven. So in the short time limit, your mean square displacement is ballistic. It is driven by inertia. But beyond the time scale, it becomes, in the long time, it becomes diffusive. So if I plot your x square average, how does it going to look like? It will look like if I do a log plot, for example, initially you'll have slope like this, isn't it? This is t square, and then so this is like t square. Is fine? Fine with all of you?
Yes.
Yes, sir.
And this part is called ballistic, and this part is called diffusive, long time limit. So your Einstein's treatment did not give you ballistic, but here the Langevin's treatment had given you ballistic motion. Now if I ask that question, what will be the answer? You got my question, all of you? All of you got the question?
Could you repeat the question?
My question is, in the Einstein treatment, we got a mean square displacement to be diffusive. No? But here, we see a diffusive regime in the long time limit, but short time limit, I get a ballistic kind of dynamics. Why? Why not in Einstein treatment?
So because we have neglected the random the kicks there.
Hmm?
We have neglected the random kicks in the Einstein treatment.
No, no, no. It is not because of that. And in Einstein treatment also, it is hidden. The noise is there. Without noise, you cannot have a distribution. But the point is, Einstein treatment was in position and time. But here, we are doing this treatment in phase rather. We have position, velocity, and time. So if you had started, if you have, if for example, if you have Einstein treatment in the phase where you have position, velocity, and time, all three, okay, position and velocity, that is called Fokker-Planck treatment. If you do the Fokker-Planck treatment, you'll also get this ballistic regime. So this ballistic regime is very short-lived. You go back and see. This is like this. If you have a very large mass, what will happen? This quantity is very short-lived, isn't it? So
Yes, sir.
yeah. So for a very large object, this regime is very short-lived, and that dynamics is called overdamped dynamics. But here in the Langevin description, I had this. Where did he start? I had this. If we had started by dropping this at the very beginning, that no inertia, I am only minus 6 pi eta RV equals to noise. 6 pi eta RV equals to noise. That is called overdamped Langevin equation. Had I started with the overdamped Langevin equation, I would have got only this diffusive region, not the ballistic. It is because we have started with underdamped, which basically means by keeping the inertia term in the Langevin description. You understand this term? If you don't have this term, if I put this term equal to 0, then I would have got this. So a Langevin description without inertia, it will have something like 6 pi eta r, v means x dot equals to this. That would have given you only this. No ballistic. Okay, no ballistic. But here you have got a ballistic thing, isn't it? So this ballistic thing is coming because you have inertia. If you had not taken inertia, your ballistic thing would have not come. If you had assumed that the viscosity is so high that inertia can be ignored, this is large viscosity limit. Okay. So with that, we'll stop today. I don't want to continue because it is already quite heavy. So in the next class, we'll go further and we want to do what is known as Fokker-Planck equation. And then we want to discuss what is known as Cramer's problem in this time-dependent statistical mechanics, which is very important, the barrier crossing problem. All of you know in this transition state theory, chemists would know. We'll try to do transition state theory, not the usual way, it is some other way, using time-dependent statistical mechanics, the physicist way of doing transition state theory, or the chemical physicist way of doing transition state theory. Okay, so we'll stop here. Okay, I'll just stop.
Thank you, sir.